Hopefully everyone had a great morning full of great talks, and we're about to get a couple more great talks. We're starting today with Tom Marble, who's talking on Clojure, designed for performance. Mr. Marble is best known for being on the core team at Sun Microsystems that open source Java. Most recently, he has launched Informatique Incorporated, a consultancy to leverage his electrical engineering background, along with his software development experience, for clients in such domains as electric vehicles, smart grid interoperability, probabilistic model checking, autonomous cyber defense. I'm glad he's doing it, not me, because I can't even say the names.
Skip the rest of that.
Multiplayer online gaming and highly concurrent software design. Mr. Marble is an enthusiastic open source software contributor and specialises in Clojure and the Debian GNU Linux distribution. He is also passionate about the legal context which makes free software and free culture possible. He has been a speaker at Java 1, DebConf, Ubuntu Live, OzCon, FISL and FOSDEM. So thank you very much, Mr. Marble. He will be talking to us and he will be taking questions at the end, at which time, if you want to ask a question, put your hand up and wait for me to run around with the mic so that we can get it on the AV. So please give a warm welcome to Mr. Marble.
Thank you very much, Rachel. And thank you very much for having me and everyone that's coming here today. Let me give you just an overview of what I want to talk about. I apologize that the screen is flickering a little bit, but hopefully it won't be too hard to read. I want to just give you a sense of what it is that I think are the pluses and minuses with Common Lisp and with Java, and how they come together, I think, in an interesting way with the Clojure programming language. Then I want to spend some time in particular about concurrent programming, because that's one of the most interesting parts or interesting features of Clojure. And then I'll talk a little bit about the future and take your questions. So, as Rachel said, I was, among other things, I started at Sun in the performance team for Java, and one of the things that I did was continuous performance integration for the JVM itself, and participated in the Spec JVM 2008 benchmark. Then I got involved with OpenJDK, which was the open sourcing of the Java programming language. Oh, it's the connector. Okay. As Rachel mentioned, I've now got a consultancy where I get to do fun things like this all the time. And in particular, one of the things that I'm doing these days is I'm doing some programming for a client in Common Lisp. Common Lisp is actually a really old language. This goes back to the 50s, and this is John McCarthy, who is the original developer of Lisp. So what is it about Lisp that makes it an interesting programming language? Well, let me just take you through some of the features that I think that make it really strong. Probably the most important one is that it's what we call, say, homoiconic. That is, the code looks exactly like the data. Of course, as you may know, Lisp stands for a list processing language, and so in Lisp, everything is a list. Both data is a list and functions are a list. And that leads to some really interesting properties, interesting things that you can do with the code. One of the things that you can do is that you can write macros that do substantial code transformations at the time that you load in a function. In particular, because the form of the code and the data all looks the same, you can have macros that actually modify and do, let's say, instrumentation on the code without actually changing the source code. One of the ways that we describe that is that writing a code walker to actually traverse the code tree is actually trivial in Lisp, where otherwise you might have to parse a language and construct an abstract syntax tree and so on. Another reason that Lisp is a great language is that it lends itself to writing what we call domain-specific languages. I'm sure most of you that have done coding have ended up writing a domain-specific language at one time or another to solve a particular problem. One of the ones I heard a talk at the International Lisp Conference a couple of years ago that really struck me was a talk on the satisfiability problem, where this is a common computer science problem, and it's often very difficult to get a really optimal result. And what this researcher had done is use Lisp to construct a DSL to express an algorithm for the satisfiability problem, and gave it to a genetic programming algorithm that just tried different approaches to it and was able to beat the best human hand-coded SAT problem by about 10%. Another thing that is really important about Lisp is that you have this thing called the read, eval, print loop. And what that means is that you can enter functions and operate on your data in a live way. It's sort of like you're actually communicating with the virtual machine that is running your code. And I'm actually going to be doing a lot of live hacking with the REPL, so you'll get to see what that looks like. And there are a number of important successes, commercial successes of Lisp. As you probably know, it's been used a lot in artificial intelligence. One company you might not have heard of is called ITA, which was acquired by Google. They are an entirely, or I should say mostly, Lisp shop that has done an amazing algorithm for airline routing and reservations. And so regardless of which travel agent you might have used or which website you might have used, ultimately it's probably touching some common Lisp software in the background to help with routing your journey. Now there are some downsides to common Lisp that I think that are worth pointing out. One of them is there is a standard, but there isn't really a compatibility test kit. And so I'm not expecting you to read this chart. The idea here is that on the columns there are multiple implementations of common Lisp, and on the rows there are multiple benchmarks. And as you can sort of see from this matrix, there are a lot of blank squares where not all of the implementations are meeting all of the benchmarks. And here you see that sort of in a larger way. So another problem with Lisp is a common problem with programming environments, and that's the library problem. How do you express packages and modularity? How do you bring in other features into common Lisp? And the common Lisp community has really struggled with a couple of different ways of doing this, and there really isn't a consistent way that common Lisp developers express a modularity, and that makes development, frankly, a lot harder. One of the things that I think that I'm really keen about is, or really interested in, is portability. One of the downsides with common Lisp is that it's often written as a native interpreter, and that means that there's a lot of hand-coded assembly involved. And as you see in this chart for SBCL, which is a common open source implementation of common Lisp, there are a number of operating system architecture combinations that just simply don't have any implementation at all. And finally, when we get to what we really care about for performance and parallelism, the tools for concurrency are actually not part of the ANSI Common Lisp specification. And so implementers often implement this in subtly different ways. And so that makes doing concurrency in Common Lisp a little bit difficult. So there are some things about Java that are important. Let's talk about some of the advantages. Obviously, the cross-platform nature of Java is a big strength. I think a lot of us know that it's not really write once, run it everywhere as much as it is debug everywhere. But even at that, it's really nice that someone else has done that hand-coded assembly for you for the very specific operating system architecture combinations. And porting to new architectures is relatively straightforward, as there is now in OpenJDK a just-in-time compiler that uses zero assembly language. And of course, Java has a rich set of libraries. It's been used by enterprises. Probably the big thing about Java that makes it great, I think, is the Java virtual machine. There is an awful lot of really cool engineering that's gone into the JVM to do things like on-the-fly profiling, optimization, de-optimization, dead code elimination, and that is the kind, and also concurrency and multi-threading. And those are the things that make the JVM a great basis on which to do, to write other languages. Oh, and another thing that's a real strength of the Java platform is the strength of garbage collection. There are many different garbage collectors to choose from in the JVM, and all of them have, or most of them have been tested and debugged and work quite well. In fact, that's, I think, led to kind of a renaissance in languages that do dynamic memory allocation, is that now garbage allocation is getting better, especially with languages on top of the JVM. However, there are some problems with Java. Probably the most important challenge with Java is that when we're trying to do parallel programming, that mutations or having procedures that have side effects, it's almost impossible to avoid that, just by the way that the language is structured. You end up having to, when you're using standard library classes, you're ending up using objects that have mutations in them, and that makes it really difficult to have thread-safe Java programs. Another large criticism of Java is that it's got such an emphasis on object-oriented programming and the single inheritance hierarchy that everything seems to have to fit into that object-oriented paradigm. For example, there's a library called java.lang.math, which is living as an object in the an object in the object hierarchy, but it really is just a grab bag of static math functions, and that's an example of sort of a strange fitting of the code into the way that Java wants to structure things. I think the best comment I've heard about Java is that it really fetishizes complexity. I won't take you through all of the APIs that you might need to know when you're doing enterprise programming. There may be a quiz later, so please keep your JSR numbers in mind. And there's more, and there's more, and there's more. But what about Clojure? Clojure is an implementation of a Lisp on top of the JVM. And part of what you get with Clojure is easy interoperation with Java, because obviously it's on top of the JVM. It happens to run as well on the CLR, and there's also an implementation of JavaScript, which is quite interesting, but I won't try to cover that today. So for example, what I'll do for just a second is I will jump over to the REPL, and here I'm calling a function, which is a Java function that I'm denoting by the dot, and I'm calling it on the instance of the string hello. So 2 uppercase is a function you can call on a string object. And so that is quite sensible. There's really an easy way to work with Java-related libraries and programs from Clojure. So part of the reason that Clojure is so nice is that the way that the objects are designed and the way that you can write functions is that they're designed to facilitate immutability, to facilitate functional programming. And there have been a number of people that have talked about functional programming here, and one of the reasons I think that functional programming is so attractive is that it allows us to do concurrent programming in a much easier way when we know that there aren't going to be side effects. So now let's get into some examples of code, starting with multi-methods. So multi-method dispatch is a way of handling polymorphism without having just a strict object-oriented hierarchy. So here, where you might think of, in an object-oriented sense, having a shape with subclasses of rectangle and circle, here I'm defining 2 shapes, rectangle and circle, and then a multi-method where the method that I'm defining is the function area. And what I'm going to do is I'm going to dispatch to the function area based on the shape that it's given. So what I say here is if I'm given a rectangle, what I'm going to do is I'm going to multiply the width times the height. If I'm given a circle, I'm going to use pi r squared. And if I'm given something else that I don't know what it is, I'll just say I don't know what to do with that. So what I can do, because of the fantastic integration with Emacs, I can simply do a keystroke here, Control-C, Control-K, and what I've just done is I've evaluated this entire buffer, which is now available in my REPL. And so now, for example, I have my rectangle, R, my circle, C, and I can call functions like give me the area of the rectangle, 4 times 5 is 20. Please give me the area of the circle, pi 10 squared. And if I give it something which is not a shape, it will say, I don't know what to do. So now, that was an example of dispatching on type. Let me show you a different way of doing multi-method dispatch. This time, let's dispatch using a dispatch function. Here I have a multi-method called greeting, and I'm going to dispatch based on the locale of the greeting. So I have a greeting for French, one for English, and otherwise I will say I don't know how to say the greeting. So in this case, I'm going to evaluate my buffer again, go back into the REPL, and see I've got my French locale, my English locale, and so now I've got my Italian locale defined. Notice that I don't have an implementation of Italian in terms of my multi-methods here. So what I'm going to do is I'm going to ask for the greeting in the French locale, and I can come up and I can do that in English. And if I say ask for the greeting in Italian, it says I don't know Italian. So there's two different ways of doing multi-method dispatch. Another very interesting feature of Clojure is this idea of lazy sequences. I apologize that this is somewhat cut off, so since the whole thing is dynamic, we'll just fix this dynamically. A lazy sequence only consumes its contents, or only evaluates or computes the contents when they're actually consumed. This is really important because when you're doing performance analysis and you want things to go faster, one of the tricks that you learn is what you do to make things go faster is just don't do stuff. Just don't try to avoid doing as much computation as you possibly can. And the stuff that you have to do it as lazily as possible, only when you actually really need it. So let's look at an example of lazy sequences. So here I'm asking for a range, and if I go to my REPL, I'm going to say R is a range, like that. And if I say convert that range to a string, it says, oh, well, that's a lazy sequence. So that's sort of a strange answer. Well, how about if you give me the first 4 things of the lazy sequence? Oh, and I did it twice, so I got it twice. That's sort of funny. Or I could say, give me the 4th element, which is number 3, in the sequence, and it will do that. Or I could say, print the sequence. And here I get the entire range of 0 through 9. So I'm just showing this to set you up for the next step, my second example of lazy sequences, which is a lot more interesting, which is here. So here I have a function called random ints. This is a recursive function, and the thing that you'll notice that's wrong with this function is it's recursive, but it doesn't have a termination condition. The way that this function works is, let's say you want to compute a random number from, let's say, 0 to 100. You could give it the limit of 100, and the function says, return me, please, a lazy sequence that is the output of the following things, and print line will just simply print a line to the console saying, I'm actually working on computing another number, and it will do cons, which is a function that takes one element and adds it to the rest of a list. So it says, okay, I will add a new random integer to the head of a list of more random integers. It's calling itself recursively. This function is basically returning you an infinite sequence of random integers. Of course, that could be really expensive if you don't limit it. So what I'm doing here in this command, first of all, I'm going to evaluate that, is I'm going to say rands is, give me the first 10 of that infinite sequence. So let me go to my REPL, and I will define that. We'll go back, and I'll say, okay, now, give me the first element of that lazy sequence. Okay, it just computed the first element, which is a random number. Now I'm going to say, give me the fourth element. It did it 3 more times. The first element in the lazy sequence was already computed, so it was already ready to go. But it didn't have items 1, 2, and 3, so it had to do them right as I requested them. So now I want to count how many elements are in my sequence. And if I just make the screen bigger, we did 1, 3, and now there are 6 more. So there are actually 10 elements in our list. And if I go back, oops, and I do the same thing again, I can repeat this count, and since that list has already been computed, I don't have to do it again. And there's my list of random integers. So, functional programming. I think that what I will do is I will just say that the reason that functional programming is so important is that when you have multiple threads that are working on things, not having side effects means that you can have multiple threads operating in parallel and you don't have to worry about side effects on the side. I won't try to explain the code on this particular page. Software transactional memory is really probably one of the key features that makes Clojure unique and interesting as a language. Mainly what this is about is allowing the idea of having transactions that give you safe mutation even though you're operating in multiple threads at a time. And there are different ways that Clojure handles that. But as I'm going through the pluses and minuses of Clojure, I think it's important to mention that one of the disadvantages about Clojure is there isn't a spec, there's just one implementation. Yes, all of our eggs are in one basket. It's basically Rich Hickey who's the benevolent dictator. However, because it runs on Java and there is only one implementation, all the community's energy is around this one implementation, and it's quite a vibrant community. There's a little bit of a concern about how the evolution of Clojure libraries is going. And it's been improving a lot since I first mentioned this concern. So I think that while the library problem is still ongoing, I think it's getting to be a lot better. But let's jump into some concurrent programming. On the right side of the screen, you'll see I've got my CPU meters. I have an i7 laptop, so I have 8 cores running. Unfortunately, the functions I'm going to run for you now are not so difficult that they're going to stress the computer just yet. But I wanted to show you how threads are handled in Clojure. All I say is I say this function future, which basically means to Clojure that I'm going to return to you a value in the future based on this computation. So in the computation that I have in this example is I'm going to add together the first 10 million integers. So I've just started that as a background thread, and when I do this @ sign of the variable, I'm dereferencing it, and I get the answer, which is the result. So that was pretty quickly, but it was simply because I was typing. So if I do it again, oops, notice that it's waiting for just a second as it adds up all those 10 million numbers, and you get just sort of a little blip of CPU energy going on. A more clear example is if I have a 5-second delay, and now I'm running this value in the background for 5 seconds, and now it comes back, and I see what the value is. Now, since the I can just run this again. In 5 seconds, it will print done. So that's an easy way to do threading. Now, for my other examples I'm going to give you in just a second, I want to show you a little usage of writing a macro. This looks kind of scary, it looks kind of impressive, but let me just, maybe it'll make some sense through examples. What I'm really trying to do is define the second macro, wait futures, and what wait futures is going to do is it's going to call this first macro futures, and it's basically going to say, I want to run all of the arguments, which are computations, times n threads. So for example, whoops, what I'm going to do is I'm going to evaluate that, go back to my REPL, and now what I want to do is I'm going to define a couple functions. I'm going to define 1sec, which will wait for a second, and then it will print 1. Oh, I actually would have to run it so you could see that. I'm going to define 3 and done, which will wait for 3 seconds. And I did something wrong. Oh, 3 and done. Yes, thank you. There. 3 seconds, done. Okay, so now what I'm going to do is I'm going to start 3 threads of waiting 3 seconds and then done. So after 3 seconds, I get those 3 threads that finish. That's what those macros are doing for me. Let's try it again with just the 1 second. Oh, in this case, now I take it back. I've got 2 arguments, the 1 second function and the 3 and done. So what's going to happen is, for each of those, I have 3 threads. So after 1 second, I get the 3 threads of the 1 that are finished, and then 3 threads of the 3 second wait, and it finishes. And I'm building up for my next example. This idiom, do times, you could think of this as like a for loop for I equals 0 to, well, I is less than 4, so it just runs this 4 times. So that's what we see there. So now, this is really the important part of Clojure, is that there are several different ways that you can handle concurrency and software transactional memory. You have operations that can either be coordinated, where basically you have multiple threads that need to coordinate their actions. Operations that are synchronous, where you will wait until an action completes. Or it could be uncoordinated, where threads can do things independently. Or asynchronous, where they don't have to block each other. The one case that I'm not going to talk about is the coordinated asynchronous case. That's really much more applicable to using a database. So the first example of this would be references, which are coordinated and synchronous. So here, now that I've explained to you a little bit about how we can use that macro to create multiple threads, here what I'm going to do is I'm going to create a reference in Clojure X, and I'm going to give it the value of 0. And what I'm going to do is, in a transaction, this is a software transaction, I'm saying in the transaction do sync, I'm going to alter the value of this reference by applying this function to it. And so now if I dereference X, it's 1. If I come back and I do this again and I subtract 1 from it, you get the expected result. Now here, what I'm doing in this set of code, I will expand a little bit for you. I'm actually calling my wait futures macro 5 threads for each of these functions. The first function will do 1,000 transactions of trying to add a very large number, which is the sum of all numbers from 0 to 1,000, to X. And the second batch of 5 threads will try to do 1,000 transactions of subtracting that number from x. So when we run this, what's going to happen is there are going to be 10,000 attempts to mutate x. But we're ultimately adding and subtracting the same amount to them. And this takes less than a second to run. Who can tell me what the correct value of x should be? It should be 0, because all of those things took place in a safe, atomic way, and all of the additions were canceled out by all of the subtractions. Let's look at another case, the uncoordinated synchronous case. So in this case, now we have atoms that can operate in a thread-safe way. So in this case, an atom is a per-thread kind of metaphor. And we use this operation called swap to mutate it. The important part of an atom is that what we're going to do is we are going to retry calling this function to do the mutation if the value has changed. So you can think of this as incrementing a order number counter or something like that. Again, I'm going to use my wait futures macro, and I'm going to define a very simple set of the numbers 1, 2, and 3. And now what I'm going to do is I'm just going to do one thread of each of these two things. I'm going to sleep for 250 milliseconds, and I'm going to try to add the number 4 to the set. And then I'm going to sleep for 1,000 milliseconds, and I'm going to try to add the number 5 to the set. Let's see what happens. How does that work? Well, that's odd. What happened? It says trying 4, and then it says trying 5 twice. Well, what happened is that both of those operations started at the same time, and they both started sleeping. But it turns out that when the second operation went around to do trying 5, Clojure realized that the input value to that function had changed. So it retried it with the correct value of the atom, which in this case is the XS set, and now we have the 4 and the 5 properly added. And the last case I'll talk about very briefly is agents, which are for both uncoordinated and asynchronous actions. And here I have just a very naive implementation of a function to calculate the Fibonacci sequence. So let me evaluate that. I'll show you what that looks like in the REPL. And I'm going to compute the first 40 Fibonacci numbers. You might see a little bit of blip on the CPU. CPU 4 got a little bit busy. It took 4.6 seconds. So now I'm going to define this very small benchmark that is going to, what this benchmark is going to do is that it's going to start for the number that it's given, a number of agents, and it's going to send this Fibonacci function to each of the agents, and it will wait for all the results from all of them to be done, and it will collect them and show you the values. So if I will evaluate this. If I do one instance of that benchmark, now starting 40 agents, they've all finished, and what you get back is the result of the first 40 Fibonacci numbers. So now I'm going to do this with my handy-dandy wait futures thing, and I'm going to cause 10 threads of this benchmark to be run at a time. And now we'll see if I can light up all 8 of my CPUs. Finally, I get some money for these CPUs to actually do some work. So that's an example of launching all 10 of these threads in parallel. And what we should get back is 10 copies of the first 40 numbers of the Fibonacci sequence. There you go. Fibonacci sequence 10 times. So let me just say a couple of words. That's an overview of the concurrent programming support in Clojure. Why I think this is interesting is, in particular, I think that Java is well positioned for new architectures, and I want to call your attention in particular to ARM, because I think ARM is a really interesting case. I don't want to call out Dell in particular, but I want to put on your radar that ARM is developing a 64-bit version of their chip, and that is going to be, I think, a very important architecture for enterprises, and I'm glad to report that Red Hat has now committed to porting OpenJDK to ARM64. And what that means is if you're programming in Clojure and you've figured out how to do software transactional memory, your Clojure concurrent parallel programs will just run on ARM64 when this architecture becomes available in a year or two. Also, a lot of you have played with Raspberry Pi. One of the things that I did after I put Raspbian on my Raspberry Pi is I put on Clojure and I ran Noir, which is the Clojure web framework, and that worked just fine out of the box on my Raspberry Pi. As I mentioned, Java, the JVM, is a great platform for a number of dynamic languages. You've probably heard of many of these, JRuby, Scala, and so on. There are a lot of features in Java that even Clojure is not taking advantage of yet. I won't go into all of the detail of these, except there is one piece here I want to highlight for you, which is I want to claim it's the shortest map-reduced tutorial ever. If you can imagine this list here, my list, which is just the sequence 1 through 6, and I want to map the function, is this number even, onto the list. There's your map. You get back the sequence, which tells you for each number if it's even or not. And then you can reduce that by using the OR function across that. And you find out that, yes, at least one of those numbers is even. So that 3 lines, the shortest map-reduced tutorial you've ever seen. So let me just wrap up by saying that don't be afraid of the parentheses. Lisp is a really powerful language. You'll find that, at least I find when I'm writing in Lisp, I write shorter functions. They're easier to understand because there aren't side effects. I don't have to think of what's happening in the background. I think that Clojure is the most comfortable Lisp to write in now, largely because it's on the JVM and that we can have access to all the great Java libraries that are already out there. And we know that it will work on all kinds of platforms from big to small. Linux, of course, is the awesome operating system that makes that possible on all kinds of devices. And there are still a lot of performance optimizations to be made. But I think the most interesting thing for me about programming in Clojure is that once you get into the swing of it, you can be extraordinarily productive and handle multiple threads, multiple processes, complex mutation in a safe way. So with that, I'm ready to take your questions.
So I was just looking at the code you had there before, and I noticed that the first argument to apply, the plus, wasn't quoted. Is there a version of apply where the first argument is evaluated?
Yeah, so let's just look at that real time. So what you're talking about is I'm applying a function to, so let's do this the conventional way. If I wanted to add a bunch of numbers, I would start, in the way that Lisp works is the first thing in the list is the function and the rest of the things are the arguments. So a conventional way that I want to add up numbers is I say plus. Now if the thing that I've got is a list and it's not like that, what I can say is apply the plus function to this list, 1, 2, 3. And that will do exactly the same thing. So your question is, why don't I have to quote this plus right here? Let me think of the answer to this. Yeah, I think that that's it. I think that really what I want to give to apply is a function, and plus is a function. Yeah, it doesn't like that. Yeah, so typically you have to be a little bit careful. For those that aren't Lisp programmers, the quote basically says, don't evaluate this, take this as a literal. And in the case of apply, plus? Oh, sure. It's a function. Yes.
John. All right. He's here. Sorry, the test that you just ran where you used all 8 of your cores, can you briefly show us that again?
Of course. So this is what I was doing. Time basically is a function that will just report the total time that I spend doing stuff. Wait futures will create 10 threads of whatever functions I pass in.
Yep.
And then remember, wait futures is a macro, so that's why I don't have to quote in this case the thing to be evaluated here, because it will just transform that code to look like the way that the macro looked. And so the 10 threads of running the benchmark function.
Right. The benchmark function, when you ran it once, had a runtime of about 4 seconds.
Yep. Yeah. So let's see. Let's see if we can go back to that. There.
And when you ran the 10 threads,
I see where you're going. Yeah. So the question is, really what you're getting at is, well, if I'm doing...
What's the overhead there? What's happening?
Right.
Why did it take so long?
Great question.
So, yeah.
I'm actually happy that you asked that question. So, okay, if it takes 3.2 seconds to do one, I'm doing 10 times the amount of work. It's sort of arbitrarily 32 seconds worth of work, but I've got 8 cores. So maybe I should get, if it was perfectly linear, I should get that done in, 8 seconds. Right. So it's more. It's 26 seconds. It's 26 seconds, but it's less than the 32. And I think that what we're seeing, right. So I think that what you're seeing here is there's a lot of artifacts of starting up, and there is definitely there is some infrastructure in handling the agents that are behind the scenes. I think that when you get to a more substantial problem, and then the time of the test isn't dominated by the overhead of setting up the agents, then you will get a much better scaling.
Do you have 8 cores, or do you have 4 cores?
I'm sorry, I can't hear you?
Do you have 8 cores?
Yes.
Or do you have 4 cores in hyperthreading? Because hyperthreading doesn't scale in hyperthreading.
Oh, it's an i7, so...
That's proxy for you.
Well, let's see. Yeah, it's probably...
Yeah.
What we can do is we can do CPU cores 4. So maybe so you're saying that that's probably a limitation to the linear scaling.
Yeah, it'll be a big limitation.
More cores are better.
So when you had the example where you did the STM transaction and then it rolled back and tried it again,
Yeah.
I noticed that you're printing out when you're trying. So my question is, what if you're doing something other than printing it out? Say maybe you're reading some input from the user and then doing something with it in the transaction, and it rolls it back and reads from the user again. Is that a problem? Is that something that you run into when you're writing this kind of stuff, or do you just keep it all separate? And
well, it's I/O is a really tricky thing because that obviously involves state mutation to handle I/O. It's probably a bad example. I mean, I don't want to cheat and say it's a bad example, but a more common thing is, as I mentioned, where you may want to... Right. Yeah, or you want to enter a new order for a new transaction and you want to get an atomically increasing number. You can basically, this is basically the sort of the compare and swap operation that's accessible to you. So you can say, you can have 100 or 1,000 or 1,000,000 threads trying to increment that transaction number, and what will happen is, the function is, take the current number, add 1, and get it back to me. And if it changed from the time that you entered the call and you exit the call, it will retry. So that's really the common use case. I know Joey's been doing a lot of work in Haskell, so you know a lot about STM.
I have a two-pronged question. Do you know what work has been done for the Clojure implementation to use the new invoke dynamic feature in Java? And do you think it would make a substantial difference to performance, or that it has?
It's a really interesting question. It turns out that actually, Rich Hickey has been very cool to the idea. I can't quite fit this URL on the screen, but I will make my slides available and under my hashtag or under my Twitter and Identica handle @tmarble. So you can get all these links and so on. Charlie Nutter, who is the guy that works on JRuby, so another language on top of the JVM, wrote this blog post saying that Clojure could actually really benefit from invoke dynamic. So I think that has not really even been explored yet. That is exactly one of the things that I think is yet to be seen. You know, can Clojure really benefit from that? And the other ones that I'll just mention by name are the fork join framework, which is the new Doug Lee concurrency thing, and the other one is tail call optimization to make recursion a little bit less expensive.
This is a bit of a two-parter too. First of all, there was a CLR port of Clojure. Is that still healthy? Is it Java only?
It's not a port that's interested me a lot, so I haven't followed it too closely, but I think it's been kind of dormant.
Okay, and yeah, so one of the things about that people in the Common Lisp crowd say is, well, when things fail, you get a Java stack trace, and it's hard to map that back to the Clojure source. Is there anything on the horizon to fix that?
Right. So the thing about Common Lisp, and unfortunately to some degree with Clojure, is that the stack traces can be really scary and awful. So out of the box, when you start programming in Clojure and you make a typo, it gives you this really scary 100-line stack trace, and you think, I just broke my computer. But the good news is there are some neat hooks that you can use to pretty print the stack traces to be much more concise and much more friendly. So there are examples of ways that you can really sort of massage that. So out of the box, yeah, you get ugly stack traces, but with this one stack trace interpretation library, it can be made a lot more readable.
Okay, we'll just take one more question and then we'll go for a 5-minute break. So who wants the last question? No one? Okay. Well, I hope everyone will join me in thanking Tom for a really great talk. It was very informative. Thank you, Tom.
Thank you so much.